Hey guys, today we're going to learn how to find the derivative of polynomial type functions along with sine and cosine functions using some shortcuts. So first let's look at these graphs. Now for the first one we have f of x is equal to 2x plus 1, which is linear, and that's why you see the line. For the second one we have f of x is equal to 2, which is a constant, so you have that horizontal line. Now remember that a derivative represents the slope of the tangent line at any point along the graph. For linear functions, such as these, the derivative is equal to the slope of the line. If you look at this linear function, the slope of this line, whether you look at the graph or at the equation, is 2. See, if you look here, if I choose this point and this point, it would go up to right 1. Or if you look at the equation, the slope of the line is 2. For a constant such as this, the slope is 0. Therefore, the derivative of f of x is equal to 2 would be 0. So based on this thought process, if f of x is equal to c, where c is any constant, then the derivative would be f prime of x is equal to 0. So the derivative of any number that's by itself is always going to be 0. Now let's have a look at some polynomial type functions. I'm going to go ahead and find the derivative of all of these functions using what's called a power rule. Now hopefully you'll be able to notice what the pattern is for these. For f of x is equal to 3x squared minus 2x plus 3, the derivative is going to be 6x minus 2. For f of x is equal to negative 5x to the third plus 2x squared minus 3x plus 1, the derivative is going to equal to negative 15x squared plus 4x minus 3. For f of x is equal to 6 minus 3x to the third plus 6x to the fourth, the derivative is going to be negative 9x squared plus 24x to the third. Now I didn't work these out before. I'm not using the limit of the difference quotient, which is what we learned was the definition of a derivative. There's actually a pattern to this. First of all, the derivative of any number by itself is always 0. So that's why here the derivative of 6 is 0. The derivative of negative 3x to the third is negative 9x squared. And the derivative of 6x to the fourth is 24x to the third. What you should be noticing by now is that how we get these terms is we take this exponent and we multiply it with the constant. 3 times negative 3 is negative 9. And then to get the new exponent, we subtract 1 from the exponent that we had. 3 minus 1 is 2. And if you look here at 6x to the fourth, we do the same thing. 4 times 6 is 24. And then the derivative of x to the fourth would be x. And then the derivative, subtract the 1 from the 4, you get 3. If we continue using this pattern, the derivative of the following function would be negative 1 times negative 2 is 2. X, subtract 1 from the exponent, so negative 2. Then to the next term, negative 2 times 3 is negative 6, x, and subtract 1 from the exponent, negative 3. For the next one, we have f of x is equal to 3x to the fifth minus 2. The derivative of 3x to the fifth, we take the 5, multiply it with the 3, so 15, x, and subtract 1 from the exponent, which is 4. Minus the derivative of any number is 0. So this would be the derivative. Lastly here, f of x is equal to 5x minus 4x to the negative 4 minus 1. The derivative of 5x would be, even though we don't see an exponent, it's 1. 1 times 5 is 5, x to the 0, plus 16x to the negative 5. Now x to the 0, anything raised to an exponent of 0 is 1. So this would be 5 times 1, which is 5, plus 16x to the negative fifth. Anytime you're finding the derivative of a term that is just x, the derivative would be the coefficient that is attached. So like I said earlier when I started this is called the power rule. Now just so you understand what this notation means, when you see d over dx, that's an operator, which means find the derivative of whatever is next to it. So d dx, the derivative in terms of x, that's what that means, of x to the n, this is the power rule. We take the n, whatever the exponent is, and we multiply it to whatever coefficient is in front. So here will be n times 1, so n times x, and then the new exponent would be n minus 1. You subtract 1. Now in order to apply this power rule, your function has to be written in polynomial form. These are examples of polynomial form and non-polynomial form. Polynomial form is when you have one term added or subtracted to other terms, versus non-polynomial form, which is here, for example, where we have multiplication, or here when we have division. So sometimes it's, in order to find a derivative, we're going to need to rewrite our polynomial. So for this one, we have f of x is equal to 2 over x squared minus 4x to the third. In order to find this derivative, I'm going to need to rewrite this in polynomial type form, meaning I can't have any fractions like this. If you have a term in the denominator that is x or some variable raised to an exponent, you can bring it up from the denominator by making the exponent negative. So f of x here would equal to 2x to the negative 2 minus 4x to the third. Now I'm ready to find the derivative. Negative 2 times 2 is negative 4. X, subtract 1 from the exponent, so negative 3. Minus 3 times 4 is 12. X squared. This will be my derivative. For this next one, we have f of x is equal to 3x to the fourth minus 3x squared minus 2x all over x. Again, in order for me to find this derivative, I need to rewrite this in polynomial type form. So what this means is that every single term in the numerator is divided by x. So 3x to the fourth over x minus 3x squared over x minus 2x over x. As a reminder, when we're using properties of exponents, when you have one term divided by another with the same bases, which all of these all have a base of x, you're going to subtract the exponents. So f of x is going to equal to 3x to the fourth over x to the first power, which is 3x to the third, minus 3x minus 2, because here my x's would cancel. Now I'm ready to find the derivative. And this is going to equal to 9x squared minus 3. For the next one, this is also not written in polynomial type form because we have these factors multiplied together. So we're going to have to multiply everything out before I can take its derivative. So let's FOIL the first two terms. We will get f of x is equal to x times x, so x squared. X times 2 is 2x plus 3x plus 6. And this is going to get multiplied with x minus 1. Before I multiply this out, I'm going to combine like terms here. So I get x squared plus 5x plus 6 times x minus 1. Now I'm going to distribute this, and I would get x to the third minus x squared plus 5x squared minus 5x plus 6x minus 6. Now let's combine all of these like terms to get our final function. So that would be x to the third plus 4x squared, because I'm combining these two. Negative 5x plus 6x is plus x minus 6. Now we're ready to take its derivative. So f prime of x is going to equal to 3x squared plus 8x plus, now even though we don't see it, we do have a 1 here in front. So this would be plus 1, and the derivative of any constant is 0. So this is my derivative. Last one, we have f of x is equal to x to the third minus 5x squared over x to the fifth. I need to write this in polynomial type form. So everything is divided by x to the fifth. So that means that x to the third is over x to the fifth minus 5x squared over x to the fifth. Remember that we're going to subtract these exponents. So f of x is going to equal to x to the negative 2, since 3 minus 5 is negative 2, minus 5x and 2 minus 5 is negative 3. Now we're ready to take that derivative. So f prime of x is going to equal to negative 2x to the negative 3 plus 15x to the negative 4. And this would be my answer. Now I'm not going to make you rewrite this if it had like using only positive exponents, but if you wanted to, this would be the same thing as saying negative 2 over x to the third plus 15 over x to the fourth. Remember that if you have a negative exponent, that just means that it's in the wrong spot. So a negative exponent in the numerator means it belongs in the denominator, and you can change that exponent to positive. Or if you have a negative exponent in the denominator, then you can move it up to the numerator, and again, changing that exponent to a positive. Now, when we're trying to find the derivative of sine and cosine, the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. So these are two that you're going to need to remember. Now I put here on the side, it's important to note that if you are finding the derivative of these functions and there is a constant attached, the constant just tags along. So for example, here I have the derivative of 3 cosine x. The derivative of cosine is negative sine x, and that 3 is just going to stick to our answer. So it would be negative 3 sine x. So let's start putting all of this together. For this question, we're going to find the equation of the tangent line to the graph of the function at the given point. We have g of x is equal to 4 sine of x plus 3x squared when x is equal to pi. So remember, the first thing that we need when we're trying to find the equation of a tangent line is that point of tangency. So we need the g of pi. So I'm going to plug that in. 4 sine of pi plus 3 pi squared. Now 4 times the sine of pi is 0, plus 3 pi squared. So this gives me, this is 4 times 0, which is 0, so we get 3 pi squared. This is my y value, and you don't need to go through and get what this number is. You can just leave it like that. So our point of tangency that I'm going to hold on to for later is pi, comma, 3 pi squared. Now we need to take that derivative. So g prime of x. Remember, we're finding the derivative because then I'll need to plug in pi to get the slope of my tangent line. So g prime, the derivative of sine, is cosine. So for the derivative of this part, it would be 4, because remember, the number just tags along, cosine x plus 6x. Now we're going to plug in pi. So g prime of pi is going to equal to 4 cosine pi plus 6 pi. The cosine of pi is negative 1. So 4 times negative 1 plus 6 pi, which gives me negative 4 plus 6 pi. This is my slope. You don't need to, again, put this in the calculator and get the number. You can leave it like that. All of these questions are meant for you to do without a calculator. So we're going to just leave our answer. So now to write the equation of our tangent line. So remember, the equation of the line is y minus y1 equals m times x minus x1. This is my x, this is my y, and then this is the m. So we're going to write our equation. It would be y minus 3 pi squared is equal to my slope, which is negative 4 plus 6 pi, times x minus x1, which is pi. And this would be my answer. Let's try a couple more. We're going to find the equation of the tangent line for each of these functions. For the first one, we have f of x is equal to x plus 2 over x when x is equal to 1. So first we need our point of tangency, so f of 1. And that's going to be 1 plus 2 over 1, which is equal to 3 over 1, so 3. So my point of tangency is 1 comma 3. Now we're going to find the derivative. Before I can find the derivative of this function, I need to make sure that it's written in polynomial form. So this means that we have x plus 2 all over x, so x is over x plus 2 over x, which is equal to 1 plus 2x to the negative 1. Since I brought the x up, make the exponent negative. Now we're ready to find the derivative. So f prime of x is going to equal to, the derivative of 1 is 0. The derivative of 2x to the negative 1 would be negative 2x to the negative 2. Now before I can plug in 1, I'm going to need to rewrite it so I only have positive exponents in order for me to evaluate. So this equals to negative 2 over x squared. Again, because we have that negative exponent, we bring it down to the denominator. Now we plug in the 1 to get the slope. So f prime of 1 is going to equal to negative 2 over 1 squared, which is equal to negative 2 over 1, so negative 2. So I have my point, I have my slope. The equation of my line is going to be y minus 3 is equal to negative 2 x minus 1. Moving along to this one here, we have g of theta is equal to negative 2 cosine theta plus theta squared over 2 when theta is equal to 0. So we want to find the equation of the tangent line. So first I need my slope of tangency. Now remember, theta is just another variable, just like x or y or z or whatever. So we just treat it like a variable. I'm going to plug in 0. So actually I should fix this here. We're going to look for a point of tangency. So g of 0 is going to equal to negative 2 cosine of 0 plus 0 squared over 2. The cosine of 0 is 1. And 1 times negative 2 is negative 2. 0 squared is 0, divided by anything is 0. So this is my y value, negative 2. So my point of tangency is 0, negative 2. Now let's take the derivative. G prime of theta. The derivative of cosine is negative sine. So negative 2 times negative sine will make it a positive 2 sine theta. Plus, now this is Remember, we take the 2 and we bring it to the front, so we will multiply with the coefficient, and my coefficient here is 1/2. So 2 times 1/2 is 1, so theta, and then subtract the 1 from the exponent, which is 1. So this is my derivative, 2 sine theta plus theta. Now we plug in 0 to get the slope, which would be 2 times the sine of 0 plus 0. The sine of 0 is 0, plus 2, times 2 is 0, and then plus 0, everything is 0. So I have my slope, I have my point. We can put it in our equation of the tangent line. So y minus -2 will be plus 2 is equal to the slope, which is 0, times x minus 0. Now this looks really strange, but you can leave your answer like that. This is acceptable. However, you could also have written y plus 2 equals 0, and then solve for y, so y would equal to -2. Doesn't matter. But either you leave your answer like this or like this. These are two acceptable forms. This one is point slope form. This is slope intercept form, more or less. And this here though is not the equation of a line. Like this is not an acceptable form. So either you leave it like this or you go all the way and solve for y. Finally, we're going to talk about horizontal tangent lines. So here, given the equation of a function, how might you determine the values at which the function has a horizontal tangent? Now, if you think back to that first slide, we saw that the slope of a constant line is 0, and that constant line is a horizontal line. So that means that if we're trying to figure out when a function has a horizontal tangent, that means that its derivative, since remember, derivative represents the slope of the tangent line, would equal to 0. Now here, if I look at this function, at which values of x will the function f of x is equal to x to the third plus x have a horizontal tangent? Now, our horizontal tangents occur at maximums and minimums, okay, because that's when, like, if I look at this function here, even though we're not there yet, you see this is a horizontal tangent and this is a horizontal tangent. Everywhere else would be some kind of diagonal line. So our horizontal tangents only occur at the extremas of our graph. Based on this graph, it doesn't look like we would have any horizontal tangent. So let's try and see what happens if I were to try to solve using the equation. If we have that f of x is equal to x to the third plus x, then the derivative f prime of x is going to equal to 3x squared plus 1. To figure out the x value, because that's what this says, at what values of x will the function have a horizontal tangent, we would make our derivative equal to 0. And then we would solve for x. So I would have to subtract the 1, so 3x squared is equal to -1. Divide the 3, so x squared is equal to -1/3, and then square root both sides. But when I square root to solve for x, I get the square root of a negative number, which if you remember from last year, this means that we have I. And I is not a real number, I is the imaginary unit, so therefore this leaves me with no solution. So this would mean that there is no horizontal tangent, which is what we suspected, because when you look at this graph, we notice that there are no extrema. Versus here in this question, we notice that we have 2 horizontal tangents. So I can expect that my equation here would leave me with 2 answers. So I'm going to solve for theta, which is for the function here where it has a horizontal tangent. So we take the derivative, f prime of theta is going to equal to, now we have 2 times the derivative of sine, which is cosine, so 2 cosine theta plus, and the derivative of theta is the constant that's attached, so 1. To figure out when this has a horizontal tangent, we make our derivative equal to 0. And now we solve for theta. So first we're going to subtract the 1 to both sides. So 2 cosine theta is equal to -1. Divide the 2. We get cosine theta is equal to -1/2. Now to figure out what theta is equal to, theta is going to equal to the inverse cosine of -1/2. And an inverse trig, if you remember, is when you're looking for the angle that would give you a cosine of -1/2, which you would use your unit circle for. So theta, if you look at your unit circle, let me actually pull one up right now. If you look here at the unit circle, what we would do is look for the angle that would give me a cosine of -1/2. So I scan here, cosine remembers the x value. This is the -1/2, and the angle is 2 pi over 3. So this is a solution. Now if I continue to search my unit circle, we also have a cosine value of -1/2 at 4 pi over 3. So those are my two solutions, 2 pi over 3 and 4 pi over 3. So we would have horizontal tangents when theta is equal to 2 pi over 3 and 4 pi over 3. So in conclusion, we have horizontal tangent lines when the derivative is equal to 0, again, because the derivative represents the slope of the tangent line and the slope of horizontal lines is 0. So that's why you take the derivative and you make it equal to 0. And that's it.